Okay, so in this section, section 6, we're going to be talking about derivatives as rates of change. And what we're really talking about here is just application problems of the derivative. We've seen about 5 sections worth of calculus now where we've learned how to find derivatives of polynomials using the power rule. We've learned how to rewrite things. We've learned a product rule. We've learned a quotient rule. We've learned about e to the x and its derivative. Now it's time to bring all that together and try to make some sense of it with some real applications. So I have 3 of them here that I'd like to go over. And the first one that we're going to talk about is throwing a stone. So suppose a stone is thrown vertically upward from the edge of a cliff on Earth with an initial velocity of 32 feet per second from a height of 48 feet above the ground. The height in feet of the stone above the ground, t seconds, after it's thrown is, and we have s of t equals negative 16t squared plus 32t plus 48. So whenever we see s of t, we know that's going to be displacement. So this is our displacement. Now, back in, I think, section 3, I spoke about displacement, velocity, acceleration, and their relationships when it comes to derivatives, which we're going to be using in a little bit here. So part A says, determine the velocity of the stone after t seconds. So remember, our velocity is going to be equal to the first derivative of displacement. So for part A, all we have to do is just find a derivative of s of t. So that's going to give me negative 32t plus 32. So there is part A. It's just the velocity. Now, part B says, when does the stone reach its highest point? Well, if you think about the motion of a stone, we know this is on top of a cliff, and please excuse my amazing artistic ability here. So here's a cliff, and the problem does say that it's thrown vertically upward from the edge of a cliff with an initial velocity of 32 feet per second. So we know the rock is going to go up, and then it's going to go back down. We also know that when the rock is initially thrown, it has a velocity of 32 feet per second, which means that the slope of the tangent line is positive. So we know it goes up, and whatever goes up must come back down. Now, the maximum height is going to be right here. So that's going to be our max height. And if you think about the relationship of the shape of the displacement, it's a parabola, and the velocity, the height of this rock is going to reach its maximum height when our velocity equals 0. Because our velocity initially is going up, then it's going to reach a max height, and then gravity is going to pull it back down to Earth. So since we go from tangent lines that are positive to negative, that means we must have had one moment in time. The instantaneous rate of change is going to be equal to 0. So all we have to do is take our velocity, set it equal to 0, and just solve. So to solve this, I just subtract 32 from both sides. That's going to give me negative 32 equals negative 32t, and then divide by the coefficient of the variable term to give me t equals positive 1. So to answer the question, when does the stone reach its highest point? Reach its highest point at 1 second. Okay? Now, letter C says, and I need to scroll up here a little bit, it's at the top of your screen, what is the height of the stone at its highest point? So here's what we know. We know that, and I'm going to try to erase some arrows here. I'm going to go back to my drawing. Get a different color. Here we go. So we know that the stone is going to reach its max height at 1 second. Now, this is very crude, but I can go ahead and label my axes, t and s of t. And I know along the x-axis, that's going to be my independent variable. At 1 second, I reach the maximum height. So I can find s of 1 by using my displacement equation, because remember, they're asking us, what is the height? So since we know when the height occurs, all we have to do is use displacement. The displacement equation. Substitute in a 1, and then just tell us what it is. So this is going to equal, S of 1 is going to equal negative 16 times 1 squared plus 32 times 1 plus 48. So S of 1 is going to equal negative 16 plus 32 plus 48, or S of 1 equals 64 feet above the ground. All right. So there's part C. Now I'll scroll back up here for part D. So part D says, when does the stone strike the ground? Okay. So I'm going to go to draw my little drawing again. Like I said, it's such a good drawing. So here's what we know. We're on the edge of a cliff. The stone is thrown vertically upward with an initial velocity of 32 feet per second. It reaches its max height here at 1,64 feet. All right, and this occurs at t equals 1 second. What we want to know is, when does it actually hit the ground? So once again, I can be very crude with drawing this. This is t. This is S of t. I want to know, when does it hit the ground, meaning what is my x-intercept? All right. Now, to solve this, we need to take the displacement equation, because once again, we want to know at what time does it hit the ground. Okay. So S of t equals negative 16t squared plus 32t plus 48. And since this is an x-intercept, at an x-intercept, or in this case, a t-intercept, at a t-intercept, I'm guaranteed that my height, or the object in question, is going to hit the ground when S of t equals 0. So I substitute in 0 for S of t. And all I have to do is just solve this equation. And there are a bunch of ways to do this. I'm going to go ahead and just factor it. Factoring it's not too tough. So this is going to factor into negative 16 times a quantity, t plus 1 times a quantity, t minus 3. Now I use the zero product property to set each variable, or each, I guess, quantity that contains a variable equal to 0. So t plus 1 equals 0, t minus 3 equals 0. I find my two values. T equals negative 1 and t equals 3. So mathematically, this is what we're looking at. However, this is an application problem. And if you can figure out how to go back in time, please let me know. Oops, sorry. If you could figure out how to go back in time, please let me know. Because I would love to go back and maybe zig when I should have zagged, if you know what I mean. So t cannot equal negative 1. Therefore, t equals 3. So the object will finally hit the ground in 3 seconds. So we reach our max height at 1 second, and at 3 seconds we finally hit the ground. So there's part D. Letter E says, with what velocity does the stone strike the ground? Well, that's a really good question. So what we know is it takes 3 seconds for us to hit the ground. We also know that the velocity of the object is the first derivative, and that equals negative 32t plus 32. So all we have to do is say, okay, well, let's evaluate the velocity at 3 seconds. So the velocity at 3 seconds is going to be negative 32 times 3 plus 32. which means my velocity is going to be negative 64 feet per second. Now, conceptually, we need to figure out, okay, what does this negative sign mean? When I drew t and s of t, the axes, and we know that the rock is 48 feet above and it comes down and hits the ground, I'm denoting that the positive is going to be in the up direction and positive is going to be in the right direction as well. So since the object is moving down, that's why this is negative right here. That doesn't mean the object is slowing down. It just means it's moving in the opposite direction of which I specified the positive direction. When we talk about acceleration, that's when we can determine if this object is slowing down or speeding up. Okay? And then, excuse me, and then the last part F. Let me scroll back up here. Part F says, on what intervals is the speed increasing? Okay? Now, once again, this is another conceptual type question. All right? So let me go ahead and draw what's happening. So we need to come up and come down. All right? So note, I want us to note that the acceleration is always going to be negative. Now, how do I verify that? If we start all the way with the beginning equation, negative 16t squared plus 32t plus 48. We know the derivative is going to equal the velocity. So that's going to be negative 32t plus 32. If I take the derivative of velocity, that's going to equal our acceleration. And the derivative of the velocity in this situation is just going to be negative 32. Conceptually, here's what's happening. As soon as I throw this object up in the air, gravity is already working against it. So even though I'm moving up, my acceleration is moving in the opposite direction, which means this object is slowing down. We can verify that just by thinking about throwing an object up in the air. The object, and let me get out a different color here. Actually, I'll use a highlighter. So as soon as we throw the object, we know it comes up, but then it reaches that maximum height where velocity equals 0, and then it comes back down. So acceleration is always working, the acceleration in this example is always working against us. That's gravity. Okay? So if we can keep that in the forefront of our mind, an easy way to just summarize what's happening here in answering the question, on what intervals is the speed increasing? Well, the stone, and I'm just going to write out a nice sentence here, the stone will be speeding up when its velocity is also negative. Okay? Now, what that means is this. The velocity from 0 to 1 second. So remember, 1 second is our max height. The velocity was positive. However, my acceleration is negative. So that means the object is slowing down. At the maximum height, and I'm going to draw a tangent line. At that max height, my velocity equals 0. After this point, the velocity is going to be negative. We've already verified that. And the acceleration is also negative. Since these two signs are the same, the object is speeding up. It's just moving in the opposite direction of what we said was positive. All right, that's a huge conceptual question that we really need to internalize when it comes to applications. So the stone will be speeding up when its velocity is also negative, and this occurs from the interval 1 to 3. Okay? So this corresponds basically to the downwards part of the stone's trip in the air. So I hope that really drives home what's really happening here. Remember, if velocity, maybe I should just write a note here. If v of t and the acceleration are the same sign, then the object is speeding up. Okay? Doesn't matter what the sign is. If they're both the same sign, the object is speeding up. If v of t and a of t are opposite, then the object is slowing down. Okay? So the next example that I'd like to look at is going to be average and marginal cost. With this example here, the directions are pretty clear. They want us to find the average cost and the marginal cost. We'll call this part A. Part B, determine the average cost and the marginal cost when x equals some value. And then letter C, always interpret the values that were obtained in part B. So before we can go any further, I need to define what the average cost is. So average cost is going to equal C of x with a bar above it. That's how we define average cost. And that's just going to be the cost itself divided by x. So for part A, to find the average cost, what we're going to do is we're going to take our cost function. So, sorry, I made that bar way too wide. So the average cost is going to equal 1,000 plus 0.01x, all divided by x, which simplifies down into 1,000 over x plus 0.1. So this is the average cost. The marginal cost is nothing more than the derivative of the cost function. So our derivative of the cost function. Now, we need to go back to the original cost function. So the derivative is just going to be 0.1. Okay? So here's our average cost. Here's our marginal cost. Pretty straightforward. Part B says, determine the average and marginal cost when x equals some value a. Well, in this case, our value of a is going to be 2,000. So at a equals 2,000, we have the following. Our average cost is going to be the average evaluated at 2,000. So that's going to be 1,000 over 2,000 plus 0.1. So 1,000 over 2,000 is 0.5 plus 0.1, which equals 0.6. Okay? Now, the marginal cost which we know is our derivative, and we're going to have to evaluate this at 2,000. It's just 0.1 regardless. Okay? So, part C, what they want us to do is interpret these values. Okay? So, when we think about this, we're going to do the average cost first. So, the average cost per item when producing 2,000 items is about 60 cents or 0.6. Okay? For the marginal cost, this is how we interpret the marginal cost. Now, this is a little bit different. So let me first label marginal cost. For marginal cost, it's going to be defined as the cost of producing the next item, which means the 2001st item, okay, is 10 cents. Now, here's what's happening here. The average cost just gives me an idea of how much on average it's going to cost me to just produce 2,000 items. The marginal cost is that instantaneous rate of change. So I know if I go from 2,000 items to 2001, it's going to cost me an additional 10 cents to produce that. The average cost takes all 2,000 items into consideration. However, the marginal cost just tells me how much to make the next one. Okay? For the last example, we're just going to be looking at velocity from position. So I just have like a nice little question here with A, B, C, and D and a nice graph. There's really not too much to calculate here. This is going to be all about interpreting slopes of tangent lines, intervals of increasing or decreasing, stuff like that, okay? So part A, let me start from the beginning. The graph of S equals f of t represents the position of an object moving along a line where time is greater than or equal to 0. So part A says, assume the velocity of the object is 0 when t equals 0. So what they're saying here is we're starting off at the origin. For what other values of t is the velocity of the object equal to 0? Now, you got to remember, velocity is the derivative. So velocity is the derivative of displacement, s of t. So when they're asking when the velocity equals 0, what we're really asking for is where are the horizontal tangent lines? That's what we want. So our horizontal tangent lines are going to occur at t equals 1, and I'll just draw a little horizontal tangent line, at t equals 2, and it looks about, I'm going to say that's t equals 3. So for part A, t equals 1, 2, and 3. That's where we have horizontal tangent lines. Now the second part asks the question, when is the object moving in the positive direction, and when is the object moving in the negative direction? Okay? So remember, if we're defining t and s to be, in the positive directions, which, let's be honest, that's how we always do this in quadrant 1, quadrant 2, quadrant 3, quadrant 4. We've all seen this before. We assume quadrant 1, t and s, or more generally, x and y are positive. So we want to know when is the object moving in the positive direction. All right. And this occurs when the slope is positive. So let me go ahead and write that here. So that's part A. Part B, the object is moving. So I'll write the object is moving in the positive direction. It would be great if I could spell. All right, so here's a nice little sentence that kind of just describes everything I was just talking about. The object is moving in the positive direction when the slope of the position is also positive. Now, this is going to occur, and let me highlight it here for us. So this occurs here from 0 to 1, and it also occurs from the interval 2 to 3. So to answer the question, when is the object moving in the positive direction? It's going to be in the interval from t equals 0 to t equal, let me be more specific here. I'll write it underneath. Positive t equals 0 to t equals 1. Another way to abbreviate this is 0 to 1. And then the second half is going to be, well, when is this moving in the negative direction? So in the negative direction, it's going to go from 1 to 2, and from 2 to anything greater than 3. So to show that, the negative direction is going to be from t equals 1 to t equals 2, and then anything greater than 3. Now, you may be asking yourself this. Well, in the positive direction, we know it's from 0 to 1. Oh, I forgot the other part. And, sorry about this. And 2 to 3. So, you may be asking yourself, well, notice that 1 appears in both a positive and negative. Well, you got to remember that, number one, I'm using parentheses and not brackets, which means I'm not including the 1 in my interval. All right? Number two, at t equals 1, we have a horizontal tangent. So at 1, 2, and 3, the slope or this object is neither increasing nor decreasing. It's, for that instantaneous moment in time, it is equal to 0. It is not moving in the positive nor the negative direction. So make sure that when you're writing these intervals, you're using parentheses and not brackets. So this is going to be from 1 to 2, or we're just going to say t is greater than 3, which another way to write that is just 3 to positive infinity. Okay? So now part C. What is part C? Oh, sketch a graph of the velocity function. So what I'm going to do is just erase what I have here. All right, I'm going to try my hardest to keep this nice and neat. It's not going to be too hard. So I'm going to come directly underneath. There's 1, there's 2, there's 3. Now, remember, this is going to be our velocity. So what I'm really concerned with here are slopes of my tangent lines. I know at t equals 1, 2, and 3, my velocity is equal to 0. Therefore, on my velocity curve, at t equals 1, 2, and 3, I must either cross or touch that t-axis because my velocity is equal to 0. Remember, all these points are all going to be t comma v of t. So if my velocity is 0, then that's going to occur at t equals 1, t equals 2, and t equals 3. Now, for the first part, all my slopes of my tangent lines from 0 to 1 are all positive, which means on my velocity curve, they're going to be above the t equals 0 line, or I'm sorry, the v of t equals 0 line. So they're all going to be up here. And I know eventually I'm going to have to come down and hit this. Like, I know that. Okay? Now, after that first interval from 1 to 2, right here, all my slopes are negative, which means I'm going to be underneath my axis, my t-axis here. So to clean this up a little bit, what I'm going to do is just bring it down below. Now, from 2 to 3, all my slopes are going to be positive. So that means that I'm going to come up and cross. And then from 3 to infinity, all the way down here, all my slopes are negative, which means I got to come around and come back down. Okay? Now, later on in chapter 4, we're going to learn about this thing called inflection points. Okay? And what I'm going to do right now is I'm going to give you like a little hint. Right here and right here, put them in blue. These are going to be the inflection points of S of t. Meaning, and I'm going to kind of just draw like a dotted line straight up to right there, and a dotted line straight up to right there. At those points, that is when the slopes of my tangent lines are starting to go back into the opposite direction. So if you look, and all I'm going to do is I'm just going to focus in right here. All right. Well, yeah, we're going to focus right here, and we're going to just study between 1 and 2. Notice that between 1 and 2, even though all my slopes of my tangent line are negative from 1 to 2, and they are, the slopes of my tangent lines before this inflection point are going to be a little bit larger than the slopes of the tangent lines under this inflection point, meaning that you're gonna be moving in the negative direction, but eventually you got to start slowing down and turning back to the opposite way. Think about on a roller coaster. All right, you're gonna come down the hill on a roller coaster, but eventually you hit the bottom and then you got to come back up. So what's happening here at this inflection point, your slopes of the tangent lines are starting to change. Okay? And we know that because, well, when you ride a roller coaster, you can actually feel that. But don't worry, that's not until chapter 4 when we actually study the relationship between the first derivative and the second derivative, and we call them intervals of concavity. But like I said, that's chapter 4. I just wanted to give you a little introduction to that. Part D, let me get out my black marker again here. So part D just says, on what intervals is the speed increasing? Okay? So the speed is going to be increasing on the intervals, and you got to think about this. Speed increasing means that the velocity is positive and the acceleration is positive as well. So this is going to happen. So let me erase all this stuff here so I can show you. And I need to erase this stuff as well. Darken that in a little bit. There we go. That looks better. Excuse me. So the speed is going to be increasing from 0 to 1/2. So I'm going to give you that first one. I can see that. So speed is increasing from 0 to 1/2 in this interval. So there's 1/2. And down here is 1/2 as well. Okay? So if you think about this, the velocity and acceleration is positive from 0 to 1/2. Now, what that's telling us here is this. Remember that little thing I was talking about, inflection points, which I said, chapter 4, we're going to actually calculate them. We're going to really learn about them. If you look at this 1/2 right here, at this point, and I'm just going to zoom in on this again. Notice all of my slopes of my tangent line are positive. They're even positive after that point. But what's happening is after 1/2, my acceleration, think of gravity. Gravity is going to start pulling it back down. That's going to, at this inflection point, is when the velocity and gravity are kind of like equal to each other. And then gravity ends up taking over. So you're slowing down until you reach that horizontal tangent line where your velocity equals 0. So from 0 to 1/2, you are still speeding up. But from 1/2 to 1, you're slowing down. Because you know, at the very top of that mountain, you have a velocity equal to 0. Okay? So if you can see that, then we can find the other parts where this is actually speeding up. Okay? So what we're going to do is let's just take a ride on a roller coaster here. So this is 1/2. Let's see. This looks like it's about 1 1/2, which is 3/2. Oh. So that's right there. We have another inflection point right there. So that's going to be, 2.5? Okay. Another way to say that is just 5/2. And then anything after 3, it's just acceleration and velocity are going to be in the same direction. So we know this is definitely speeding up in that direction. Okay? So let's think about this. Actually, I don't even have to write the word speed. We're just going to write the word up. So we're speeding up. Then from 1/2 to 0, we're going to be speeding down. We reach this and we reach that horizontal tangent. Then from 1 to 3 halves, notice the acceleration and the velocity are in the same direction. So on 1 to 3/2, it's increasing, so we're speeding up. Then we're eventually going to hit this tangent line down here. So from 3/2 to 2, we're going to be speeding down. Then we get to the bottom, we start to come back up. So from 2 to 5/2, we're going to be speeding up. And then from 5/2 to 3, we're going to be speeding down. We hit this horizontal tangent. We know it's 0 there. And then after that, we're just going to be speeding up all the way down to 3 to infinity. So let's kind of see what's happening on our velocity curve. And let's try to relate these two things. All right. Well, notice on the velocity curve, you're coming down, you're speeding up, but eventually you need to come back around. Right here, we know that we have a horizontal tangent. So right here, you're speeding up again. So we have speed up, and then we have slow down. Then from 1 to 3/2 here, we're speeding up. And then from 3/2 to 2, we were slowing down. I need another marker. This is getting ugly. There we go. We're slowing down. We hit that horizontal tangent right there. Now we're speeding up again. We hit the horizontal tangent. Now we're slowing down. We hit that horizontal tangent one more time. And then afterwards, we're just speeding up because velocity and acceleration are in the same direction. So just to summarize everything, our speed is increasing from the interval 0 to 1/2, comma, 1 to 3/2, comma, 2 to 5/2, and then from 3 to infinity. Speed is decreasing from, now I'm just reading my graph here. So speed is decreasing from 1/2 to 1, from 3/2 to 2, and then 5/2 to 3. And that's it. So this last example here was really all about interpreting displacement, velocity, acceleration, and how are those all related to each other. If you have any questions, just please let me know. Just send me an email. But other than that, the next video, I don't even know what the next section is. I forget already. Let me look at it real quick. The next section is going to be the chain rule. So the next section, we're going to actually learn more general derivatives of like the power rule, e to the x, and some quotient rules and stuff, or quotient and product rules. So that's going to be really, really awesome. And that's about it. So I'll see you in the next video. Bye.